I'm Dhruv. I'm a PhD student at Berkeley. And to start off, I do not work in autonomous driving, so I'm not fully sure why I'm here. Um, but I'm going to talk about a somewhat related problem, which is visual navigation. So I'm a PhD student at Berkeley. I work with Sergey Levin, and I work on building algorithms and systems to get robots to move around in the real world spaces. And that's what I'll talk about. So I want to first, still working? Yes. Okay. Yeah. I want to first start off with a shout out to some of my favorite and, objectively very impressive robotic systems from the last few years. And I don't need to convince the audience here that machine learning is a good idea for robotics. And we've achieved some really, really nice feats like this, flying around in a forest and placing things and driving around in suburban streets and all of that. And these are all robots running learned neural network models on the edge and solving really challenging tasks in the wild. And very broadly, these fall under two categories. On the left, we have this really impressive agile drone flight result from Zurich. And if you look under the hood, the key to getting this to work is large-scale simulation, which is also the case for a lot of AVs today. So you need, what you start off with is you build a simulator. In this case, it's a game engine. You have high fidelity depth. You have a lot of privileged information. And while this has been a very good recipe for a lot of applications, modeling every simulation you care about at scale is really challenging in sim. It may not be possible when you want to go to completely new environments. And it can be arbitrarily hard for a lot of modalities beyond depth, like if you care about RGB or sensors that are not very popular, that may not be a very scalable solution. On the right, we have methods that rely on large-scale real-world data collection. So in this case, there's this pick-and-place robot from Google that is doing very impressive things, but under the hood, it was trained with hundreds of hours of real-world data collected by a large fleet of robots. This is great because policies trained on your robot tend to work very well on your robot. But every few years, you change your robot, you change your environments, and then all of that data becomes useless, which may not be something you want. And in general, data, when you train machine learning policies on a narrow domain of data, it tends to be very fragile in terms of perception, in terms of dynamics, and it struggles to generalize to entirely new settings. And this boils down to the challenges of why learning from real world data is hard. The real world is hard to simulate, no surprises there. And collecting data for doing real world learning can be a very high barrier for entry. If you need to collect hundreds or thousands of hours of data for every new setting that you care about, that's not scalable. Which particularly if you're working in robotics, this can be infeasible for systems like this really nice nano drone, which has a battery life of about 5 minutes. So if I need to collect 100 hours of data, I need to be swapping batteries every 5 minutes, which is not a great idea. And even if I do it, the policies are fragile because the moment something changes in the environment or my robot, things start breaking. But it doesn't need to be so hard. So at first glance, our robots are very different and they do very different things in different labs, different environments, and so on. So for instance, if you're a manipulation researcher, which maybe not in this crowd, but if you're a manipulation researcher, you may have one of a few different kinds of robots with slightly different capabilities, different morphologies, or maybe you have your own custom arm. And similarly, if you're a mobility researcher like me, you may have a lot of different platforms which are mobile robots, but they have different capabilities. Some can walk, some can fly, some can go under things, and so on. But if you zoom out enough, and some people may disagree with this, but most of their tasks are actually quite similar. So maybe not as obvious for the things at the top and things at the bottom, but between the clusters, our robots look very different, but they kind of have very similar capabilities in the sense that they need to parse visual observations, they need to plan something to the goal, execute actions in the real world, avoid collisions, maintain smoothness constraints, and so on. And fundamentally, I believe that the embodiment gap between a robot that exists in the real world and a new robot you can come up with, so they all perceive real images, they do real dynamics, but the gap between existing robots and new robots might actually be smaller than the gap between simulation and doing real robots. So sim to real is probably a much harder problem than real to real. So what I'll talk about in this talk is a slightly different way of thinking about real-world robot learning, where we focus on pre-training policies from robot data in the real world, and then we'll transfer that to other settings in the real world, so you're doing real-to-real transfer and training models completely in the real world. So our objective is to train something that can be a good starting point, like a plug-and-play policy or a zero-shot policy, and something that you can, just go to the internet, go to GitHub, download that policy, which in this case, we call it a general navigation model. You download this policy, and then without much effort, it just works out of the box. And not just that it works zero shot, but it can also be a very good starting point. So to solve a task that you really care about, you would fine tune this model with a small amount of data, let's say for a new sensing modality, or for a new goal that you care about, or for new robots that you come up with that were not in your original training data, or for new tasks, new objectives, new reward functions, and so on. So I'm going to kind of talk about two aspects of this. First, what is a good objective and a setup to train this kind of a model? And then how do you use this model for a lot of downstream applications? And before going a lot further, I tend to use this phrase called a robot foundation model. And this is a word we throw around a lot these days. And there's a lot of different interpretations for what I mean by this. So I'm going to define what I mean for this talk. And then at the end, maybe we can debate different interpretations or how else to think about it. So I'm going to define a foundation model for robots as a model that once you train it, no matter what you do, once you've trained it, it can be used zero shot, can be deployed in different settings, on different robots, different embodiments, different tasks, and so on. But it can also be adapted in a fairly efficient way. It can be adapted to another downstream task of choice. And in this case, that would be different other embodiments, other ways of specifying the goal, other objectives, and so on. And this is kind of the definition around which this talk will go, but then we can revisit it or challenge it at the end. Great. So as a quick overview of the talk, and I'll try to be a little bit shorter so I can make up for the AV goof up. I'll talk first about what it takes to train such a cross-embodiment backbone, the foundation model that I talked about, using hundreds of hours of existing real-world robot data. And this data is collected from different robots, different embodiments, different environments, and so on. Next, I'll talk about how this policy can also serve as a starting point for a range of downstream applications by fine-tuning or adapting it with different sensing modalities and different applications. So one of the things I'll talk about is, while you can train a very general policy at the end, you would not be maximizing the capabilities of your hardware. So there was a poster here about training racing policies. What if you care about doing really high performance policies from images? How do you fine-tune this to get those kind of applications? And at the end, very briefly, I'll talk about how you can fine-tune this model to do other interesting tasks like learning with humans in the loop to do socially compliant navigation. Let me first describe the general setup for everything in this talk. So, let's say you go to an environment, the robot has not been here before. You drop your robot, and this could be an outdoor robot or an indoor robot, whatever. I'm trying to be a little agnostic to that fact. But let's say you have this new environment, you drop your robot, and the robot has an onboard computer. So whatever you do runs on board. There's no cloud here. And the robot has a single camera, which is a forward-facing RGB camera. And you can assume you have access to, okay. You can assume you have access to some proprioception, let's say local odometry, other local observations. But for the duration of this talk, I'm not going to get into other sensing modalities. I hope that the ideas would extend to other modalities, but for now, we're going to think about a shared, very simple sensing, which is RGB cameras, and you're going to go from images to actions. And given these things, and you have some sort of a goal, which could be specified as an image, as language, as some other commands, it could be a trajectory to follow, whatever. And you want to build a backbone that can be used for all of these tasks. And I want to put a big disclaimer up front that these assumptions and the methods that I talk about, they're not prescriptive. And in no way am I saying that RGB is all you need or this is the right modality. But I'm suggesting that this is a way to solve a task. And if there are other modalities we care more about, we can change it up. By the way, I'm not monitoring Zoom, so if there's anything, let me know. Great. So let's get started into the first segment, which is training the backbone. And broadly speaking, for any machine learning problem like this one, there's three sets of challenges towards training a machine learning policy. It is developing algorithms for training these models and where your data comes from, which is collecting and assembling large robot data sets that actually have the right set of features and labels that you care about. And of course, designing the right architecture, which is both kind of general to do everything, but it's also really good for the task you really care about. And it should be able to, scale up. So the more data you have, the larger you can make your models and so on. For the algorithm, we use a self-supervised objective that uses trajectory level labels that are readily available from training data. So in this case, if you have a video or a trajectory, you would take 2 sample points in the trajectory, the temporal distance between them, which is the number of frames between them. That's a free signal you have for any data set. And if you have access to actions that were taken during training, which could be expert or suboptimal, you would take these actions, and these suboptimal actions serve as a prediction target for your policy. And the objective is goal condition BC. So nothing too fancy here. On the data front, this was done in an academic lab. I was too lazy to go collect more data myself. So a big motivation here is you have a lot of existing data sets out there. You want to be able to use these data sets to train a policy. And what's the best you can do from offline data sets? So we aggregated a fairly large cross-embodiment data set across 10 different robots in different university labs, different environments, and different sizes, different capabilities. And this was data that people just donated because they had lying around. So we did not moderate the quality of the data or how it was collected, what camera it was collected with, so forth. There's some heterogeneity there. And for the model, we proposed a new transformer-based backbone that I'll get into in a bit that uses past observations and goals to predict the targets, which is the distance and the actions that I talked about. And we use a diffusion process over the future actions to represent complex action distributions, which are typically multimodal. So before we get to the model, we need data. So rather than the typical way in which we do machine learning, which is I have my robot, I go collect some data with my robot, and I train a model on data that I collect from my robot, so it only works on a single robot. We're now thinking of, well, what if we combine all of them, and you now have a large data set which is collected across different robots, different environments, and then you want to train one giant policy on all of these data sets. So we start with a standard goal condition navigation model. So this is the rough architecture we'll be playing with. The blocks will change, but the inputs are the current observation. You can have, you can have a little bit of temporal history or context, but you have observations, which are images, and you have a goal, which in this case, I'm going to stick to goal images, but then we can change that to GPS or language or whatever else it is that you care about. So you have your current observation, you have some goal observations, and you want to predict how far the goal is from the image and what actions I need to take to go there. So nothing too fancy yet. We're going to make 2 changes to adapt this model so that it can learn from these different robots and different data sets. So first, we'll abstract away the low-level controller because each robot will have different dynamics and controllers that we care about. And we're going to make predictions in some sort of a normalized action space. So this is an action space that is agnostic to the embodiment itself. And in this case, this is going to be the distance in temporal steps. So it's time steps of distance. And the actions are going to be normalized by speed. So it's kind of now this unit time notion of actions. And this helps to abstract away the variance between the different robots. As you would guess, by doing this, you lose a lot of capabilities that each robot is good at, but then we'll get into how to fine tune it at the end. But for the start, we're going to start with something very generic. And to make it better at understanding history, we will condition it on some temporal context. So in this case, you'll condition it on past observations rather than just your current observation. And the simple thing, if you just have convolutions, is you have a fixed context history and you condition them on all of them. If you have something more attention-based, which is what we'll get into, you can have a flexible window over which you can condition, maybe an infinite window as well. So how do we scale up this sort of an architecture to take more data sets, more things in the real world? So, the scale of data that I have is much smaller than the scale of data you can have if you're in industry. But we reached at about 150 hours of data, which is still a large amount of data by robotic standards, because no single lab would actually be collecting so much data. So we talked about how can we scale up our model so we can actually get to 100 hours of data, but maybe even more, because in the future, you might be collecting even more data. And we'll generally talk about 2 axes on which we can scale it up. So first, the very simple thing that everyone likes to do, which is just make everything larger, make the capacity larger, have more parameters to tune, and that gives you, more room to absorb the data. And second, doing it in a slightly clever way, how can you make your models more expressive so you can capture more complex action distributions? So for the first one, again, starting from images or a stack of images and a goal image, what we'll now do is we will pass them through a convolutional block to get visual tokens. And then we plan over these visual tokens using a transformer decoder. So this would be a decoder-only transformer that reasons over a goal, which could be an image or another modality, and your visual tokens, which are tokenized using convolutions, but you can use something else if you care. And in this case, you would use them to predict the things you care about, which is the policy and the actions. And that gives us the VINT, which is what we call the visual navigation transformer. In this case, fairly large, fairly small by LLM standards, pretty large for small robot policies which are running on the edge. So it's about 30 to 50 million trainable parameters, and it reasons over images to predict actions. And secondly, beyond just making things bigger, I guess one thing I should mention here is the reason why this architecture is very interesting is there's two main places where your parameters lie. One is your encoder, which is convolutional, and the other is your attention heads, which is a transformer. And we know by now that you can make these as large as you care. So you can make so we started with an efficient net, which is about 5 million parameters, but you can switch to your res nets, large res nets, which can go about 10x this size. And transformer blocks, again, increase the heads, increase the layers, and you can get a lot more capacity to learn with these models if you have more data. Secondly, to go beyond just making things larger, we talked about how we can make the action process better. So we take the context vector from before, and then we use a diffusion process over this context vector to predict actions in an iterative way. So we take the, okay, this timing is off. But we can now condition the diffusion process on images as well as goals to get conditional and unconditional samples from a diffusion model. And as we know by now, diffusion models are really good at modeling complex distributions that are not necessarily unimodal. And this allows us to, maybe I can replay this, never mind. This allows us to model more complex decision-making, like if you're an intersection and there's multiple possible futures, how do you represent this? Okay, and the really nice thing about starting to train these things from multiple cross-embodiment data sets is you get some sort of robustness for free. So for instance, we found that the trained model is robust to dynamical degradation, such as a pop tire, which has a puncture, or in this case, you have a piece of wood in the tire. Which really affects the dynamics of the model. So if you were just training on the dynamics of a single robot, it would completely fail because you have something that is ruining your robot's dynamics. But by training on these cross-embodiment data sets, the model realizes that, oh, it's not that important if one of my wheels has popped and I can keep going ahead. Similar observations on the perception side. So to test how robust the policy is to, let's say, the height of the camera, which is something typically a lot of learned policies fail at. If you change the height by a little bit, the robot crashes. So here we deployed a policy on a robot, and without telling the policy, we changed the height of the camera between one of 3 different heights. And if you stare at the viewpoints from the camera image, you can kind of see that it changes the image quite significantly to the point where you need to account for these things. And while this perturbation is subtle, it does break single robot policies. So in this case, we had a demonstration of going around this indoor maze-like environment to the goal. And for all different viewpoints, we found that the policy works just fine, and it doesn't really care for this. And the real takeaway from this kind of robustness to heights is we can now deploy it to a completely new robot, which was never in the training data. So we never trained this model on, let's say, aerial robots or legged robots. But then zero shot, this policy can now be put on a drone, and it navigates a hallway without colliding and gets to the goal successfully. Kind of some more videos, but I think the Zoom audience will find it more choppy. But we took our robot, which is, we now took a legged robot at Coral, which is the robot learning conference last month. And we deployed our policy on the legged robot at Coral. And I should preface this by saying that the robot was not trained on, there was no training data from legged robots, but there was also no training data around humans. So the robot actually does not know how to navigate around humans. And I was very confident that we would take it to a conference, and we didn't realize that there would be 100 people in the room, but it looks like the robot is holding its ground, and without colliding with people, it's still going. And you can, well, so sometimes it hits people, but not too bad. And you can do the same thing indoors, outdoors. Again, it's the same policy, same checkpoint along for all of these videos, all of the robots. So in this case, this is 4 different robots with different cameras, different controllers, clearly. And you specify some goal, which is something far away, and the robot kind of, the white robot is somebody else's. Ours is the good one. The one that we're following is the good one. Yes. So yeah, it's this again. The thing to note is across all the videos, it's the same model checkpoint with no changes, no fine tuning, no specific parameterization. You just put it on a robot and it's working. which is nice. It's not doing something interesting yet. This is still the base model that I talked about. Okay, I see someone's recording. No worries. um, Okay, so trying to quantify these performance improvements, what does this really mean for scaling and for generalization? So we try to compare across different robots. What if you trained a model from data from each single robot? So this is what you would do today. You have 10 hours of data from your own robot. You train your single robot model and you get some sort of a performance. And this is some weird performance metric on the y-axis. Let's ignore that. And let's just think about the height of the bars. So you have some performance that you get from your own robots. And we have two different models that I won't get into, but one is small, one is large, and they're both trained on data from all of these robots combined. And we kind of see this this improvement where there's positive transfer in that you're not only matching the best single robot performance, but you're doing better than each individual robot while still being the same policy. So you gain this generalization without actually losing performance on each of the individual robots, which is very nice, and which is usually what did not work before. So things start making more sense once you scale beyond 2 or 3 or 4 robots, because then things become a lot nicer. And as one last slide about the base model, all of this code is public. People have already started downloading and using them. And every once in a while, I get emails from people saying, "Oh, we put this on a robot in Estonia in some forest, and it's navigating a forest, mostly going straight, but not hitting things and following a lane." Or in this case, in Princeton, somebody put it on a drone. And again, this is not me. This is someone else who downloaded the code from GitHub, put it on a robot, and it works, which is kind of nice because now we can start talking about reproducibility and getting better in real robot results without worrying too much. This is another one, which is a forest and a library in Finland. And as you can about, is not doing very impressive things, but this is completely zero shot in a completely new environment on a completely different robot. And it's not crashing, which was my hope. So that's great. And this is, if you've been following the LLM land, this is kind of the unicorn test where I am giving it, for sure, I can guarantee that this environment was not present in the training data because this is a country I've never been to and I've not seen that robot and it's completely new. Okay, so while we're on the subject of generalization and robustness, I want to kind of give a peek under the hood in that why does this work or why should it work? It's no magic. It's a machine learning problem. It's a very small model. I'm not going to throw emergent capabilities in here. And in a sense, if you really look at what's happening, it's not that different from how domain randomization has been working in reinforcement learning for the last 5 to 6 years. So if you think about all of these wonderful sim to real results, you randomize the heck out of every distractor available in the environment. Like the background, the texture of the objects, the jitter, the weight of a leg of your ant, something like that. And that makes the models ignore these things that don't matter and just focus on the thing that matters, which is going towards the goal really smoothly. So by sourcing real world data from different distractor parameters, like what city it is, or what lighting conditions it is, or how tall the camera is, and so forth, you can train the model to ignore some of these distractor variables and just focus on what you think is important. So by randomizing over intrinsics, extrinsics, different turning radiuses, different speed, whatever, you now get a model that it's general in that it's learning some sort of an average behavior. I wouldn't say it's actually learning different policies for different robots, but it's learning some sort of a conservative policy across everything. And during inference, once you get a little bit of context, you have this implicit sysid thing, which is you're trying to predict the context given your past images. So in some sense, you're just trying to learn an average behavior conditioned on the observations of the robot, which is nice, and which is why it starts working everywhere. And a small kind of quantitative peek into what we'll talk about next, moving beyond just generalizing in zero shot, the thing that you really care about is fine-tuning these models. So let's say I give you a completely different task. And in this case, what we did is all the models were trained from real world data. So the best way to get a fully held out task is we went to Carla and we said, Carla is simulation. Simulation is different from real. So what if you wanted to do real to sim? So you have a budget, which is 2 hours of data, and you can collect 2 hours of expert data in Carla. And you define some task and you define a success metric on it. And let's say the task is doing a loop and staying in lane. So for that task with a couple of hours of data and some simple BC policy, you can get certain metrics, and that is the baseline to beat. So you have this 2 hours of data. Now, can training on other data sets improve this? And we compared this to, training with ImageNet pre-training, which is what people used to do 10 years ago and no one does anymore, but more kind of self-supervised pre-training methods like SimClear or VC1, which uses an MAE-based pre-training, where you're pre-training on visual encoders. And then comparing it to models that we had, which is pre-training not just the encoder, but entire policies. And we see that even though the dynamics are different and the perception is different, everything is different, pre-training entire policies, even on much less data than VC1 or ImageNet, you can get much better generalization because pre-training policies is a much better prior. And similarly, if you actually compare how fast it learns, in just about 40% of the fine-tuning data, it maxes out the task, and it's very good. Okay, so we talked a lot about this architecture and lots of things it can do. One last thing I want to touch upon, which I found really cool, was this is a transformer, and the reason we like transformers is they have a token space which is not exactly interpretable, but given once you give it some tokens, it'll do the attention magic and start working. So in the language community, one of the ways this has been working is you prompt these models to learn something nice, and then you steer the outputs using these prompts. So the idea behind prompt tuning came out, in which you can have a learned prompt or soft prompt, which can be used to adapt the model without fine-tuning the whole thing end to end. This makes a lot of sense when your models are billions of parameters and you don't want to do full model fine-tuning, and that's where low-rank adapters came around and soft prompts came around. And even though this model is not that large, we start seeing that we can do this notion of prompt tuning. So concretely, we utilize the fact that the transformer operates on this abstract token space, and one of which is the goal token. So you can remove the goal image, which is how it's specified right now, and throw away this goal image encoder and replace that with a different modality. So in this case, you could replace it with a GPS goal or a language goal, and you have another encoder that projects it back into the token space. And once you do that, the rest of the model already knows what to do given a goal token. So now you can get really fast fine-tuning by changing a very small part of your model. And this allows us to adapt the model to new tasks and new goal informations in this case. And it works. So I'm going to skip some videos and then, in the interest of time, start moving towards how can we go beyond what was in the beyond what was in the training data. So I talked about how we can learn this sort of average behavior across data sets, which is a good pre-training objective. But then eventually, let's say all you really care about is, I have a robot. Let's say you have this very nice RC car that can go 30 miles an hour, probably faster, on different terrains. And all you really care about is racing around a track. And you want to go as fast as possible. And you don't really care about all of this average case business. You want something that works really well for your robot. So in this case, this specific robot, it has, it can go really fast, and you need to learn the dynamics of the robot to be able to maximize them, to be able to drift in the corners and discover racing lines and so forth. And well, as you would expect, high-speed navigation is really challenging. People have looked at different aspects of high-speed racing, and I won't get into too much of the details there, but three big challenges I can think of is it's very hard to get very accurate localization at high speeds. In this case, again, I'm thinking about the visual navigation problem, which is you don't have very good, let's say, RTK GPS outside. You're just using your images to figure out where you are in the racetrack and finish your task. And this is actually what an RTK GPS measurement looks like for a racetrack with our car. For 2 laps, they're just so off that if you just used this as a ground truth state information, the robot would just crash every time. And visual images actually add value. But the problem is, if you look at what images look like when you start going fast, it's super blurry. The exposure is terrible. Half the image just looks white, and the rest of it looks blurry. And it's very hard to actually infer states directly from the images. And end-to-end learning makes a lot of sense for a case like this. And of course, as you would expect, the dynamics start going bonkers when you go very fast. So if you're on this, we were testing this on the slick floor in our building, and the robot just starts slipping if you accelerate too much. And you're trying to take a turn, you need to account for that slip if you want to take good turns. So we clearly don't have enough data to learn this kind of policy from scratch. If you wanted 20 to 40 hours of data to learn this from scratch, it would be very good. But I can't afford the robot crashing into things and losing its head. So what we explored is, can we use this sort of pre-training, which is what I talked about so far, to bootstrap this learning. So just as before, the first stage now would be this offline pre-training, which is this bootstrap model that I talked about in the past. And then taking this general policy as a starting point, you would fine-tune it in the real world with online data collection to maximize the capabilities of your robot. And in this specific case, we're going to do this with reinforcement learning. So we define the task, which is going really fast. Your reward signal is your normalized speed across the loop, something like that. And the thing you're trying to drive down is your lap times. So you want to go as fast as possible without colliding. And you're starting with something which is kind of collision free. Great. So I'll just kind of quickly get into some of the videos. As you'd expect when you start, the policy that I talked about so far, it's good at driving really slow going around, but the moment you start putting an RL objective and you start doing exploration on top of it, it's going to crash into things sometimes. It's going to explore different parts of its action space and mess things up. But just about 15 minutes of real world data in, and this is actually 1x. All videos are fully real time, and the robot now figures out, okay, if I want to make this turn, I need to go into the curve at a certain rate. This is happening on a carpeted floor because just so I can talk about it, and we'll go outside in a minute. Oops, why did my screen sharing stop? Okay, let me try to put it back. It'll come back. Oh, it's back. Okay. Zoom, share screen. Okay, it's back. Okay, yeah, so about 15 minutes of real world practicing in, and the robot can now do collision-free laps, but it's still exploring different parts of the environment. And about 25 minutes, it's really figured out what the right way to make these turns is. So we had a human expert who's really good at driving RC cars, and we capped the speed just because it's indoors. And in about 25 minutes of real world practicing and fine-tuning this model, you actually start reaching the capabilities of that expert driver. So this is what the onboard footage looks like. This is from a GoPro that's on the robot, not the robot's perception itself. But you can tell they're going fast. This is what the third person view looks like for an outdoor environment now. So this is a robot which can do whatever it wants to go really, really fast around a small loop around a building, which is what we made. And this is now kind of driving roughly at 6 meters per second. And one of us is running behind the robot because it's very fast for us. And this is the kind of thing. So this is actually what the robot sees indoors and outdoors. And this is kind of talking about how if you want a very special task that you care about, how do you start with that general policy and you can fine tune it to do better things. Similar curves as before, starting with different pre-trained encoders. So just doing visual pre-training to solve this task, you realize that you can solve the task, but it's still quite a ways off from a state-based or a human-based baseline, a human expert baseline, which is really what you want to maximize if you care about tracing. And we find that given the right starting point, which is a fully trained policy, and exploring on top of it, we actually can beat the human baseline and significantly outperform other ways of pre-training stuff. And on the qualitative side, we saw some very interesting behaviors. So while prototyping this in sim, we noticed that despite the objective was just this end-to-end objective of going very fast, we find that the robot learns the concept of a racing line, which is kind of visualized here with the speed marked in red color. So the robot kind of slows in before going into the turn, takes the turn, hits the apex, and then exits and goes fast again. We also find that it figures out that the right way to make a fast turn is to drift. So this is me trying to show it drifting into a slick surface while it takes a turn. And if your hand coding policies to do drifting, you would hand coding policies to do racing, you would hard code kind of these racing lines and drifts into it. And it was very cool to see that kind of just end-to-end learning, we see these emergent properties come out of it. And I don't have a video for the last one, but this is the blue line is the future trajectory overlaid on the current image. And we find that the robot realizes sticking to the path, which is paved, is actually much better than going into the grass. And even though there was no semantic signal, it figures out that the right thing to do is stick to the path. Great. I'll go into one last thing, which is another way you could fine-tune such a base policy for a very difficult task. In this case, let's say you have a robot which is going around indoors. It's doing an inspection task, let's say in an office, and you have humans in that office as well. So you want to not annoy the humans and you don't want to hit them. So very simple setup. You have a robot that is driving around a building, executing some sort of a task, let's say inspection, and you have humans that you're not explicitly modeling, but the humans are doing whatever they want. They're getting coffee, they're talking to each other, they're walking past. And you want the robot to not interfere with the humans. So definitely not colliding them, but also not blocking paths that they want to go at, not obstructing their ways, and so forth. And an important thing to note is this is kind of the first effort we're trying in this direction. So it's not really looking to model the humans, but at the level of what can I do when there are humans around? How do I learn behavior that doesn't hurt humans? Eventually, there's kind of a lot of work in the multi-agent space to do in this, but to make it very concrete, here we're talking about a robot with a camera. It only has the camera. It does not have any privileged information in terms of where the other agents are. It doesn't know the states of the other agents, and it needs to go from images, observations around the environment to actions that don't hurt the humans. And to kind of talk about what the specific learning objective looks like. So doing on time. Okay. You have your classic objective, which I'm just going to say there's a navigation objective, which is the kind of objective I talked about in the past. And then you can add a couple of things. So you can say, in addition to just getting to the goal, which is your base objective, you also want to avoid collisions. But we start a new objective here, which is called minimizing the counterfactual perturbations. So in this case, if there is a pedestrian that already has a plan and they have to go ahead in the environment, because of the robot's plan, if the pedestrian has to change their plan, so the pedestrian has to modify their plan from, let's say, the dark blue to the light blue line, that's not good. So we now have a predictive model of what the human wanted to do and what the human will do next, and you want to minimize the distance between the two. And you don't want to get too close to the humans, which is you don't want to violate any personal space. So we add these two objectives into the original objective, train a predictive model, and use that as a reward model to fine-tune the base policy, and iteratively optimize the two of them. So this is kind of done in a continual learning way, where you have a predictive model that's being updated and the policy that's being updated, and you jointly make them do things. And I think I'm going to start skipping some of these videos just so I can finish up in time for the next person. But we set up some objectives. We see how many interventions you need and blah, blah, blah. And over multiple days of deployment, interventions go down because this continual learning thing is working and all of that. Also, we did some nice user studies where we found that doing this end-to-end and starting with a good policy makes people feel nice about the robot, and the people say the robot is smooth and it's preempting our behavior and it's not hitting into things. I would get into more details of this, but okay. If you're somebody who works in the navigation space, especially for indoor robots, we collected a large data set of human interactions in this case, because now we had a continual learning system that doesn't need intervention. So it's just going around the office and doing interesting things. So it's about 75 hours of data with human-robot interactions and disengagements and all sorts of things. And you can do stuff with it. So yeah, I talked about training the base policy, training a few different ways of using this policy, and wrapping this thing up. Quick takeaways: real-world robot learning is becoming feasible, especially for small robots doing not very safety-intense tasks. And it's at this point where you can start taking this data from other people and deploying it. And you should try it out if you already work in the space. Cross-embodiment pre-training is a great idea, not just for training visual features, but also for training policy and control level objectives. And there's nothing to lose in that. You do not risk losing degradation in your own robot, but you stand to gain a lot. And online learning in the real world seems inevitable for a lot of these tasks. So starting with a good base policy and improving online is a great setting. And we talked about a couple of different ways where you can do this. Very quickly, I didn't get any time to go into other projects, but I want to highlight a few different related efforts. And if you have questions, maybe after the talk, we can talk more about this. So kind of a big effort from some of the people in our lab is kind of how do you use this cross-embodiment nature of learning beyond navigation and other tasks like manipulation, pick and place, mobile manipulation, and so on. How do you combine these policies with a natural language interface? We had a great talk from Barbara before this about what the role of language is for planning, for perception, for control, and so on. And also combining them with just high-level planning and search for doing very large-scale navigation, which in this case is the level of large city blocks and doing things in the real world. Anyway, that's all the thing I had in mind. The models, code, everything is public if people are interested, and I'll just leave some videos in the background for questions. But
Yeah, thanks for a very nice talk. I was wondering, like, is there in this framework, is there still space for simulated environments? Like, can you still make use of that in a good way?
yeah, that's a great question. I think something I think about a lot is what the role of simulation is, in that you can always train in simulation and deploy in simulation, but what does sim buy us? And I think a big thing to gain from simulation is to help with benchmarking. So one thing that you notice in this whole talk is there's a big lack of benchmarks in real world robot learning, which is if I train three models and you train three models, you'll find yours are better, I'll find mine are better. And how do I compare? How do we move ahead as a field? So something that I've been thinking about a lot is you have all of this real data, but you also have some simulated data, and you try to train, instead of thinking of this as sim to real, you do real plus sim to real plus sim, and then you evaluate this in a sim environment. And I don't think there's agreement in terms of what the right tasks are and what the right sim is. But let's say if everyone agreed that Carla is a good thing and we made a good task in it, this would make a lot of sense in terms of benchmarking. Another place where I think sim would be very useful is for going to sensor, kind of expanding to other sensing modalities. In this case, images are easy because everyone has RGB images. But if you start having different kinds of lidars, different kinds of radars, and you want to incorporate different sensors, then having them in simulation is a lot easier than having them standardized in real.
Yeah, thanks.
Thanks. Oh, I can. Okay, I'll take that next. Yeah, but you can go ahead first.
Yeah, fantastic talk. I have a question about you train a foundation model. It seems like a model which can generalize across like 10 data set, right? But now have you ever considered, for example, you provide instruction as another input so that the model will be able to kind of specialize if you provide, corresponding environmental, information. Yeah.
Yeah, that's a great question, and I think again the cop out answer here is you saw the scales I'm playing with. This is like 50 million parameter model, 100 hours of data, not nearly the kind of data you want to get these nice zero shot properties. But I think the big challenge here is the lack of good annotated data sets that you can play with. So there are large annotated data sets in robotics, but they're all usually in a small simulator, like there's a habitat thing, or maybe there's a room simulator thing. I think if we had the data set to do this, I don't see why this is like a fundamental challenge. But also there could be fundamental challenges in that you're now talking about closed loop evaluations of these things, not just predicting images or captioning images, but at the level of control in the loop. So I think there's some people working on how do you use these models kind of separately. You have language models and you have action models and you interface them, but training the whole thing together seems like we just don't have the data yet. There's some work I talked about. There's this big effort from Google called RTX, which is now talking about a million trajectories or something. But a million trajectories is not that much data. If you really think about how much diverse data it captures, it's nowhere enough close to the scale at which these kind of things start making sense. So it's early, but that is the vision for, that is the goal to aspire for. Okay, there's a question in the chat that I can take, which is, could you comment on the safety and interpretability aspects of these models and how to improve these aspects? And yeah, so I think that's a great question. Something that I've not touched upon definitely in this talk is this actually competent enough to be used in deployment scenarios? And I think safety is one of these things where even for static cases, which we're seeing with language models and vision models, it's very hard to guarantee it. But there's an empirical notion of safety, which is if you become really, really good at avoiding bad things, maybe that's good enough, even if you cannot provide guarantees. I think for end-to-end models, I imagine safety would look in a very similar way, where you would have a lot of corner cases, negative mining, a lot of annotations, and you would fine-tune these models to be really, really good to empirically be safe. But to start having guarantees, you would now have a separate stack. I don't think fundamentally just the uncertainty estimates from learned models are good enough. that we would just get this to be safe, especially when you're trying to do these things across embodiments, across environments, where we don't really understand what the scaling laws are, what the dependence on. How do you attribute a failure to which training data point so you can remove it and so forth? But yeah, it's very challenging. There's one more. Yeah, I think that was the only one. Yeah, that was the one that I answered. Yeah.
Actually, I have another question. So yeah, first of all, it's great to see all the use cases like in Finland and Princeton and stuff like that using your work. Can you like, is there opportunity there to close the loop and get that data back and like kind of work together with you know, streaming these data, new data sources back in to get a better model?
Yeah. I mean, I think yes, in that would be great. But it is, I think a part of it is just challenging because working with people needs more than just one grad student who's doing this on the side. But there's some efforts. So I think again, I draw back to the big cross embodiment initiative that Google had, which is I think the thing on the left here, where it's not just navigation, it's just taking manipulation, pick and place, grasping, mobile manipulation, all of these different kinds of data sets, and then training some large models on it. And it seems that they are opening kind of the door there in terms of you contribute data back and what you get is other people's data. So there is, I think there needs to be an entity that is willing to do this, in that you'll soon reach scales of data that a single computer is not going to hold. So you now need to have a repository to do this. And then somebody needs to gatekeep what gets in and what gets out. You want to make sure there's no malicious things where people are injecting bad data. So it leads to, you colliding your robots. And there's a whole economy that is possible, but it's probably so early that nobody would commit to doing it, in that the people that have the resources have legal obligations and the people that don't have the resources cannot do it. So it's not a good answer, but it's the right answer.
Yeah, no, thanks.